Hi, this is Professor Fernandez, and this is video 3 in lesson 13. We're still talking here about linearization, but what we're going to do in this video is work through an applied example from Calculus Simplified. So this example is going to have us use a new interpretation of the derivative. So I've put that down here, but I won't review it just yet because I want to get to the first part of the example first. So let's see what it says. The example says airlines change the cost of their flights regularly to maximize revenue. Suppose one airline's research team has found that the revenue R in dollars associated with a particular flight is modeled by this function, R of x equals a quadratic function. X here is the number of tickets sold, and that's restricted to the range 0 to 100. Okay, part A, calculate R prime of x and include the units. So let's do that. R of x is a quadratic function, so its derivative is going to be this power rule application here. Derivative of x squared is 2x. And then plus the derivative of 90x, that's just 90. So I know what R prime of x is. Great. How about the units? Well, the easiest way to remember the units is to convert this into Leibniz notation, because then the units of the derivative are the units of the output divided by the units of the input. We already saw that R was in dollars, so this is dollars in the numerator, and then X was number of tickets, so this is dollars per ticket. Right? So that's our derivative function, 2x plus 90 dollars per ticket. So now let's look at part B. If the airline has already sold 50 tickets, calculate R prime of 50 and interpret your result using the linearization interpretation of the derivative. All right, so the first part we can do pretty quickly. R prime of 50, we just substitute in 50 for x. We get 2 times 50 plus 90. That's 100 plus 90. That's 190. And then again, dollars per ticket. So great. And now interpret what this means using the linearization interpretation of the derivative. So I'm going to go over here, just review that for you before I get to that box down there. So suppose I graph a function, right? And in some sense, it's kind of like the function we're just working with, quadratic function, let's say. And I go over and I look at some a value here. There it is. So there is a tangent line that I can draw for this function like that. All right. Now, what would happen if I moved over 1 unit, right, in the x value? So in other words, I add 1 to a. Then what happens? Well, look at this graph, and let's keep track of where the y values go. This is the y value on the tangent line. In previous videos, 13.1, 13.2, we call the equation of the tangent line L of x, the linearization. So this y value here would be L of a plus 1. And the y value on the actual function, right, we would have to keep going up a little bit to here. That y value is f of a plus 1. Okay. So you notice that the change, or I should say the increase from the original y value, which is f of a, so the increase from here to the actual y value on the function is approximately the increase from the original place to the y value on the tangent line. Approximately, okay? So this goes back to this notion of linear approximation, which is what we've been talking about in these past 2 lessons. So what can I say if I were to summarize this picture? Okay, I could say this in English. When x equals a 1 unit increase in the x value results in an increase in the y value, f of x, of approximately. Okay, and now let's try to quantify this. How much would the y value increase? Well, here's the really nice thing, okay? The graph of the green line is a line, and it's a linear function, and it's the linearization, right? So because it's a linear function and it's a linearization, we know the slope of the green line. The slope is the slope of the tangent line f prime of a. Because it's a linear function, we know that in a linear function, the slope is equal to the change in y over change in x. And the slope is f prime of a. So if I multiply this equation by delta x, then this tells me that the change in y values on the tangent line is exactly equal to whatever the slope is, in this case f prime of a, times the change in the x values. If I am assuming a 1 unit increase, then delta x is 1, and so therefore delta y equals f prime of a. So that's what goes down here, approximately f prime of a. Okay, so to review what happened, what's going on here? We had a function, we picked a value, we drew its tangent line, and we observed that the increase in the function is approximately the increase in the tangent line. And we were doing all this, the presumption was we were adding 1 to the x value. So that got us here. When x is a 1 unit increase in the x value results in an increase in the y value of approximately, and then we had to quantify how much. And how much is going 1 unit to the right on the tangent line and arriving at a y value that is approximately f prime of a higher than it was at x equals a. Okay, so that's a really visual overview and in effect a derivation of what is down here. So I'm going to read this in a minute. So what does it say? This is the linearization interpretation of the derivative. Here it is again, so I'm going to sound like a broken record. A 1 unit increase in the x value a increases the y value f of x by approximately f prime of a. Okay, and now there's a qualifier if f prime of a is positive. If I go back to the picture I just drew, this green line has positive slope. I'll save you the time of redrawing this picture with a negatively sloped line, but you can see that in a negatively sloped line, if I go 1 unit to the right, my y value goes down. Okay, so the y value would decrease, right? Decrease in y value by approximately f prime of a, if f prime of a is negative. So this is the linearization interpretation of the derivative. This is at least a conceptual review of it. So let me show you how to apply it now in this particular example. So let's go off and do that. We're going to use that interpretation to interpret r prime of 50 equals 190. So I'm just going to start writing here. So I'm going to say a 1 unit increase in the x value 50 increases, and I'll say why it's not decreases in a minute, the revenue r of x by approximately, what is f prime of a here? It is $190. Okay, so what I've done is I have written out this linearization interpretation for the particular example that we're working on, and I have put in some of the information that we have. So I didn't put in all the information because I want to go step by step, but for example, the y value f of x is the revenue r of x. Okay, f prime of a, 190, that goes here. So now let me do one thing here and put in a little bit more, slightly bit more of the information. What about, oh, I guess it won't let me copy it. Okay, I'll do this. So what about a 1 unit increase in the x value? What is the x value in this problem? It's the number of tickets sold. So I'm going to erase here in the number of tickets sold. Number of tickets sold. Okay, so this is an interpretation of the r prime of 50 equals 190 result. However, if you were actually working for this airline company and you went to your boss and you gave that person this interpretation, it would be a little hard to parse, right? It's a little difficult to figure out what's going on here. So let's write it out in a different way by looking at it and thinking about what's really going on. So a 1 unit increase in the number of tickets sold 50. Okay, so we can say selling 1 more ticket after you've already sold, oops, too many L's there, after you've already sold 50 tickets. That's a different way of saying a 1 unit increase in the number of tickets sold 50. Increases the revenue by approximately 190. Will increase your revenue by about $190. This is a statement that I think if you went to your boss, if you were working at this company doing this type of work, would resonate and make a lot of sense, and your boss would be very grateful to you for this little piece of insight, right? If you've already sold 50 tickets, if you happen to sell one more, your revenue is going to go up by about $190. That's a very specific number, So that would be insight that, other people who have not taken calculus may not be able to offer. Okay, and this is an example, again, of the linearization interpretation of the derivative. This stands in contrast to the only other interpretation of the derivative that we had up to this point in the course, which was the geometric one, which said that 190 is the slope of the line tangent to the r of x function at x equals 50. That's another statement that if you gave to your boss in this context would not be very helpful, right? But this one is much more helpful. Okay, so that's part B, and now let's finish this up really quickly with part C. Because your boss might come to you and say, wow, this is phenomenal. I had no idea that this was something that could be quantified in this way, and this is a really nice insight into how the revenue changes when we sell more tickets beyond 50. But your boss might say, what is the actual change in revenue? You told me, I picked up on this word approximately, about. What is the actual change in revenue if I sell one more ticket above 50? So to do that, we're going to look at part C, and we're just going to calculate that difference. I'm going to go back to r of x, substitute in 51. That ends up being $7,191. Substitute in 50, that ends up being $7,000. And subtract. I get $191. So you'd go back to your boss and say, oh, I have the answer. The actual change in revenue is $191. So you would say to your boss, I was pretty close, right? I said that it would be about $109. So you can see, therefore, one of the uses of the derivative to approximate changes in y values when the x value changes by 1 unit. And that, in effect, is the linearization approximation interpretation of the derivative. Why do I call it the linearization interpretation? Because, again, throughout this video series, we have been talking about how f of x can be approximated by the linearization for x near a. Okay. Also, we can turn this into the change in f of x can be approximated by the change in L for x near a. And then if x is a plus 1, in other words, 1 unit increase in a, right, then that is certainly near a. So this linearization interpretation really does fall out of the linearization work that we've been doing. And beyond the details I've given in this video, you can find more of those details in Calculus Simplified around this example, right? There's a discussion preceding that gets us to this linearization interpretation. Thanks for watching.